I would like to talk about some of the work we've been doing on trying to understand the frictional mechanics of shallow slow slip events. And I'm hoping that this will be a somewhat integrated perspective, looking at some experimental data that we've generated, some numerical modeling work, and some field-based observations. So just to kind of get started, right, so we've known at this point for a couple of decades, I think, right, that fault slip at plate boundaries is accommodated in a variety of ways, from creep, slow slip events, tremors, LFEs, all the way to dynamic ruptures and so on. And so I'm sure this audience especially is very familiar with this, and so I don't want to really belabor this point too much. In this talk specifically, I'm focusing on fairly shallow slow slip events, up dip of the traditional seismogenic zone, very near the trench. So my goal is to understand what physical and mechanical conditions allow slow slip events to sustain at so many plate boundaries around the world, and what this means for strain accumulation at the shallowest reaches of the plate boundaries, particularly at subduction zones. Okay, so I've divided my talk into two parts. So in this first part, I want to talk about fault healing and frictional stability at a shallow slow slip source. Which if you were in Tamara's talk last week, you may find a little bit that this is a bit of a continuation or perhaps related to her results. I also want to give a quick shout out to the paper that a majority of this part of the talk is based on, and this was just published last week, so please go check it out if you can. So particularly for those in the audience, perhaps who weren't in Tamara's talk last week, I want to give a very brief primer on fault healing and restrengthening between earthquakes. So on the left-hand side here, maybe you can see my cursor, is a cartoon of shear stress evolution over time, sort of in the simplest sense. When the stress accumulation in the fault reaches its strength, the fault is going to slip. During an earthquake, the fault experiences a stress drop, and post-seismically, we need to have some sort of recovery, strength recovery mechanism, because otherwise the fault is not going to be able to host another earthquake, for example. So this post-seismic strength recovery is what I'm calling healing. And depending on if you are a, mechanicist or field geologist or seismologist, you probably have different definitions of what this healing is composed of. So because I study earthquake mechanics primarily in the lab, I'm interested specifically in frictional healing of geomaterials. Okay, so I want to introduce a very simple framework first to think about healing. So between earthquakes, a fault is going to heal in some fashion. If it's frictional healing, which is what I'm talking about right now, we typically view it as a log with time process, which I'm showing in purple here. The other component of this puzzle is sort of the far field tectonic loading, which wants the fault to fail and competes with the restrengthening. So to a first order, we can assume that the loading component is linear in time. And so when the fault is loaded more than it can heal, we experience an earthquake. So this framework gives us some sense for the recurrence interval in time and an upper bound on the stress drop that we can probably observe during an earthquake. So I'm going to take this framework and apply it to shallow slow slip events in New Zealand. Okay, so why New Zealand? I want to briefly touch on the tectonic setting in the Northern Hikurangi margin, offshore Gisborne, New Zealand, and talk a little bit about why this is so special. So here, you have the Pacific plate subducting beneath the Australian plate at about 52 millimeters per year. And what makes this an interesting region to me for research are these very repetitive quasi-periodic shallow slow slip events, which repeat every 1 to 2 years, averaging about 18 months recurrence interval. They last for a few weeks and rupture or slip a fairly large area, which is what these slip contours represent, in very small stress drops and small total slip, which is what I'm showing you in these panels here. So you can see the stress drops are, off the ballpark of under 10 kPa even, and the slip duration is a few weeks on average. So one of the unique things here maybe is that we have an excellent record of SSEs, shallow slow slip events, going all the way back to 2002, and also some IODP drilling, which recovered materials that we think are participating in these shallow slow slip events here. So we have materials that could be representative of the shallow slow slip source. So this is an example of the materials that were recovered from the drilling, and what we found and what I want to point to, what that is really interesting about these materials, is that they are compositionally extremely heterogeneous. So we're specifically interested in the green stuff here, which is identified as Unit 5. And this is all altered volcaniclastic conglomerates. And the alteration products here are mainly smectite clay minerals, taking up anywhere between 20-ish to 80% of the total composition. Okay, so in this slide, I want to very quickly talk about the reason for specifically focusing on these volcaniclastic. So this is a recent paper published in Geology by Andrew Gase and others at the UT Institute for Geophysics, where they show, using high resolution reflection seismic data, that the shallow plate interface at the SSE source here in the northern, as well as sort of the north central Hikurangi margin, is forming in these volcaniclastics. And so this is where we're basically seeing the shallow SSEs, and that's why these materials are important and relevant and interesting to us. So based on these observations in the field today, I'm asking the question whether frictional behavior of this SSE source material, whether it can explain shallow slow slip at the northern Hikurangi margin, and if so, how? Okay. So to answer these questions, we ran friction experiments on the SSE source material in a pressure vessel with pore pressure under a fairly realistic in situ stress conditions. Because this is the shallow portion of a relatively colder margin, we're not too worried about temperature at this point in these experiments, although I am going to talk about that briefly at the end. To provide a broad overview, we saw significant healing on the frictionally strong carbonates, which may be more important as we go south along strike, along the margin. But here in the north central margin, the volcanics are frictionally super weak, the more important material, and they basically show little to no healing at all. Next, there you go. Okay, so here I'm showing you the frictional healing data from the lab experiments on these clay-rich volcaniclastics in the context of other common materials and plate boundaries, like say quartz or carbonates, specifically in the plot on the left. There you go, there's my cursor. So beta is the log linear slope of frictional healing rates, and typical numbers for the stronger materials like carbonates, for example, are in the ballpark of 10 to the minus 2, which is in units of friction change per decade of time. And so this is also a pretty popular choice, say for numerical models, for example. However, best we can tell, the healing rates for our volcaniclastic materials, which are these purple and green dots down here, is probably at most about 10 to the minus 4 per decade, and very likely even lower than that for a range of effective normal stresses that we tried. So the shaded areas are for other clay-rich materials to recover from other regions, say, for example, the San Andreas Fault. And generally, what we see, or what we can conclude from this, is that the clays, and particularly smectites, keep healing rates very, very low. The plot on the right has the same data on the stress drop space over a longer x-axis. And we convert this healing data into a stress drop by multiplying it with an effective stress. And so these are the different effective stresses or different pore pressure ratios that we attempted to convert this frictional healing into a stress drop. So just for your reference too, I also have plotted these brown squares are the stress drops, the average stress drops of the Gisborne Northern Hikurangi SSEs. And these gray triangles are stress drops from the Calaveras Fault repeaters, just to give you a sense for how drastically different SSE stress drops are relative to, I don't know, let's say ordinary dynamic ruptures. And so the frictional healing rates of these materials are also very consistent with this. Okay, so going back to this framework, based on the friction experiments, let's say we have some real constraints for this purple curve here that constrains healing, but estimating the loading rates or stressing rates from plate convergence rates for subductions and geometries is typically not a super trivial task. And so we're estimating loading rates in a couple of ways I'm going to show you in this talk. First, sort of the easy method that gives you a broad bird's eye view on the inter-SSE stressing rates is here. If we take this excellent record, almost 15 years of slow slip events at Gisborne, simply take the ratio of the average stress drop to the recurrence rates for these events, you get something that represents the loading rate, which is in the ballpark of 5 kilopascals per year. So this represents a slip patch averaged loading rate and indicates to a first order that the shallow megathrust experiences super low loading. The other way in which we can get at this is through numerical modeling, because we know the relative plate velocity in this region, and we have very good geometries and seismic velocity models from reflection seismic surveys and so on. So we took all this information and ran a finite element modeling pilot to see what that looks like in terms of a stressing rate on the shallow plate interface during inter-SSE locking. So the log portion of the fault is the super shallow portion right here, which represents a depth of up to 15-ish kilometers. So the way we do this is we implement this as a static numerical model with layered heterogeneous elastic properties and impose the total annual convergence, so about 50 millimeters, as slip on the subducting plate, so that the stress accumulated at the shallow locked portion of the interface gives us the stress accumulation number that represents an annual stressing rate. So when we do that, these are the results that we get. The top plot is simply a cartoon just to have a frame of reference of the shallow plate interface. And this bottom plot shows the results from our pilot model. So overall, the model is predicting pretty low loading rates, about half a kPa near the trench, all the way up to maybe 28 kilopascals per year at a depth of about 14 kilometers. So these estimates of loading rates we got from geodetic observations in the previous method are in the red box here. And overall, both techniques are in very good agreement and give us an average of about 5 to 10 kilopascals per year of loading in the shallow megathrust in this region. So in the next slide, I'm going to show you a snapshot of this competition between loading and healing that I'm talking about at 3 representative depths, so at 25, 50, and 75 kilometers from the trench. Okay, so we're looking at the competition between loading, which increases linearly with time, which is the black curves in all of these plots, and frictional healing, which increases logarithmically with time, which are the green, orange, or purple curves. So we convert the frictional healing into a stress change by multiplying the healing rates with an effective stress. In this case, I'm assuming the pore pressure ratio is 0.9. So pretty overpressured, but not really quite at the lithostat yet. And we do this for 3 different values of healing rates that are nearly 0, but lower than the upper bound that we constrained from our lab experiments, which was about 10 to the minus 4 per decade in time. So again, just as a reminder, the point where the loading and the healing rates intersect gives you a recurrence interval and a maximum for your stress drop for these boundary conditions. So for example, for the orange curve across these 3 plots, you have a loading and healing intersecting at about, 1 to 3 years on average, and that fails in about 4 kilopascal stress drops, which is quite similar to what we've documented for the Hikurangi area shallow slow slip events. We can also take this a step further and define what I call a strength excess. And you can think of this as being somewhat similar to a Coulomb stress change concept, but conceptually here, the frictional strength is increasing with time. So the strength in this model at any time is simply the difference between how much the fault has healed and how much it's been loaded at that time. So for example, if the strength excess, if we're at 1 year here for the green curve, the fault has healed more than it's loaded. So you have a positive strength excess. And so if we go here, for example, after 3 years, the fault has been loaded more than it's healed, so it's going to fail. So that's a negative strength excess, and so on. We can play this game and do this exercise basically all along the plate interface, along the shallow plate interface, I should say. And so that's kind of what I'm showing you here in these 3 plots for the 3 healing rates that we looked at. And so this plot has strength excess on the y-axis after 1, 2, and 3 years. And you'll note how it's pretty small, versus distance from trench along the x-axis. So a majority of the SSE source region is colored in gray. And what you'll see is that it has a nearly 0 strength excess for between 1 to 2 years. And what this means is that this area is ready to fail. So this indicates that basically a broad region of the shallow plate boundary may be primed to fail. And because the slip and strain deficit that you can accumulate over 1 or 2 years is quite small for this type of a scenario, we'll naturally end up with slow slip events that have tiny, tiny stress drops and small amounts of total slip, but those that rupture a broad area. And so just restating what I've said so far is basically that a combination of the low tectonic loading rates coupled with nearly 0 healing rates is resulting in very frequent low stress drop SSEs, which have small total slip and rupture a broad area. Okay, so then what about effective stress? Because the argument generally is that the slow slip source probably has nearly lithostatic pore pressure. So we can do this exercise again for a range of effective stresses. And that's what I'm showing you here. What that does is basically it modulates the amount of healing over time, because remember, healing in this framework is a product of the healing rate times effective stress. So for pore pressures that I've arbitrarily chosen, to be 0.8, 0.9, and 0.95, I'm showing you this sort of plot for different healing rates. The only combination I will say out of these 9 combinations I've tried that doesn't fit the Northern Hikurangi margin slow slip events is this first scenario of the highest of our low healing rates and relatively high effective stress. Other than that, pretty much 8 of these 9 scenarios do a pretty decent job of fitting the shallow SSEs observed at the Northern Hikurangi margin. And so this framework predicts the SSE stress drops and recurrence intervals pretty well, even if your pore pressures are not quite near lithostatic. So, okay, we can combine all of these observations. And I like to think about a couple of different scenarios for healing rates, because the healing rates typically depend on stress and temperature and a whole bunch of other parameters. So here I've plotted time and slip predictable simple models for what slow slip events would look like at, say, 25, 50, and 75 kilometers from the trench, 25, 50, and 75. If we only had, on the left, I'm considering a constant healing with depth scenario. And on the right, I have a scenario where I'm increasing the healing rate with depth. So I will say I personally favor the scenario on the right, the black curves, where you have increasing healing with depth, because in the shallow portion, even though the margin is relatively cold, you can expect somewhat increasing temperatures, and that could modulate healing rates, and they could be driven by this. So what these plots are showing us is that in the case where you have increasing healing with depth, going from relatively low healing near the trench to higher healing rates at the SSE source, you could have slow slip events very, very close to the trench, like this x equals 25 case here. And because of the incredibly low loading and healing rates, we're probably going to get super frequent, tiny slow slip events that will probably just look like creep in the geodetic record for a land-based GPS station. And so what this says is that probably we need ocean bottom or downhole sensing instruments very near the trench on the upper plate to really see how the strain is being accumulated and released near the trench. Okay, so far, I've only showed you healing and how that points to these materials hosting frequent slow slip events. Now, we could also take a look at the frictional stability of these materials in sort of the rate and state friction world, and you'll see that this is also completely compatible with slow slip events. So this is a plot of the rate and state frictional stability A minus B on the y-axis and the critical slip distance D sub C again on the y-axis in this plot, both plotted as a function of the velocity, step velocity of rate and state friction experiments. And what I want to point to is simply that both A minus B and D sub C increase with velocity. And what this means is that the nucleation of an instability in this region is potentially rate limited. And so we can think of the slow slip events, you can recast them as prematurely arrested nucleation of an instability. So particularly taking an example of the critical slip distance, for example, if that increases with velocity, this implies that the critical stiffness reduces, or if you're in the H star world, the critical patch size H star is increasing with velocity. Energetically, this is going to favor a slower rupture over a more dynamic one. So taking this just one step further, you could ask the question of why does D sub C, the critical slip distance, why is it increasing with velocity? So in my mind, there's a couple of possibilities that I'm sharing here. These are two sets of velocity step experiments on the same fault, on the same material. One is pressurized on the left, and the other is room dry on the right. That is the only difference between the two. In both cases, D sub C increases with velocity. So black curve is the lowest velocity, orange is the highest velocity. And the increase in D sub C with velocity is given in these as these bars here. The magnitude of the increase, though, is more pronounced in the case of a pressurized fault than it does in the room dry case. So it's possible that inherently the critical slip distance D sub C encodes information about the shear zone width and delocalization, and adding water and pressurizing the fault further enhances this potentially through dilatant strengthening or something of that sort. And that's my working hypothesis for the velocity dependence of D sub C. Okay, so finally, I also want to show the really cool data set from KJ Im and others, which is numerical models that incorporate the velocity dependence of friction A minus B and D sub C. And so this really nice study shows basically that incorporating velocity dependence of frictional stability produces slow slip events in models. And this mechanism also, interestingly, does not necessarily require near lithostatic pore pressure, although it definitely helps. Okay, so just to summarize this first part of my talk, what I've showed you so far, and hopefully convinced you somewhat, is that the competing effects of low healing rates and low elastic loading rates of the upper plate allows recurring shallow slow slip events at the Northern Hikurangi margin and potentially elsewhere globally. And I think that's kind of important because these clay-rich materials are somewhat ubiquitous everywhere in the shallow plate interfaces. And so this kind of a framework could be applicable somewhat more broadly as well. The other interesting thing is that high pore pressure or low effective stress keeps the restrengthening quantity, the beta times effective stress, low. And this provides an additional mechanism by which low effective stress could help sustain slow slip events. The other important result to come out of this is this idea that, that incorporating the heterogeneities in the upper plate elastic properties play a significant role in determining the loading rates. So for example, in our numerical models, I guess I kind of forgot to point it out, the elastic properties of the upper plate as constrained by seismic velocities, the rigidity is of the order of 10 to 15 gigapascals GPa. So that's significantly lower than the usually assumed 30 GPa crust rigidity. And if we consider this beta term, the healing rate term, to be equivalent to the B term in rate and state friction, earthquake rupture simulations, importantly, should probably consider significantly lower values of B to represent the phyllosilicate-rich, clay-rich shallow SSE patches that may be prominent in shallow plate interfaces everywhere. So in the second part, I want to talk about slow slip events generated in the lab and how we simulate them numerically. So this is work in progress, so you may find that it's a little brief, but I am super excited to share some of our results with this audience. Awesome. Yeah, so in this sort of figure on the left, I assume some, maybe many of you in this audience have seen this before. This is work from John Lehman and others, where they basically vary the effect. So going from the top to the bottom in these lab experiments, the effective stress is reducing, as you'll see, from 14 to 6 MPa. And what that does is, at the high effective stresses, you get fast stick slip events in the lab. And as you drive the stress lower and lower, the effective stress of the normal stress in the fault, you get slower and slower slip events, smaller events that finally result in stable sliding, which is not pictured here. But if you went even lower than 6 MPa, you just have stable sliding. These types of observations on lab faults typically come from 5 to 10 centimeter long faults. And the general view in the community, I guess, has been that they're rigid spring block sliders, meaning that the entire fault moves all at once at the same time. So when you reduce the normal stress, what you're doing is you're making the critical stiffness or K sub C smaller, or increasing the effective stiffness to move across a bifurcation. So numerical models that incorporate a one-state variable friction law typically reproduce this behavior super well. So you can see in this 4 snapshots for numerical model results, you're increasing the normal stress going from this bottom one to the top one. And at the bottom case, you have stable sliding at the low effective stress. As you increase the effective stress, you get slow slip events that are sustained, and eventually you get these faster stick slip events with larger stress drops and so on. So some experiments, particularly I find in gouge or finite thickness faults, as I'll call them, show a lot of rich complexity near the bifurcation, near where K equals K sub C, or where this fault stiffness is equal to a critical stiffness. And you get all kinds of period modulating behavior. So you might get 2 period cycles, 3, 4 period stick slip cycles, all the way down to chaos, where the stick slips are no longer periodic and well behaved. And this happens very close to the stability boundary. And this is a data set that we've generated, which also shows the same thing. So there's a friction experiment, same shear stress data plotted versus time in the top panel versus displacement in the bottom panel. And what I want you to look at specifically is this inset, where as we increase the effective stress, you have stable sliding until you reach a point where you have these super chaotic, not well-behaved, aperiodic stick slip events. Now, these behaviors are not typically captured in the standard one-state variable friction law. And what you need is something more, I guess, sophisticated to model them. Using more state variables, for example, 2-state variable, 3, 4-state variable friction laws will reproduce this behavior. But the problem with that is we don't fully understand the physical basis for 2 or more state variables in friction laws. And so what I'm showing is a somewhat different modeling framework that you will see is able to capture these behaviors pretty well. Okay, first, a close-up of the lab data and the lab friction experimental results. To kind of understand this chaotic behavior. So this is a single direct shear friction experiment with quartz gouge shear. So this is a quartz gouge actually of thickness about 3 millimeter wide, and it's sheared between two steel plates of area 5 centimeters by 5 centimeters. And there's also an external spring, which is kind of important because it helps modulate the, it helps modulate the system stiffness and helps drive it lower. And in the bottom, I'm showing you the shear stress evolution for data generated through this experiment for a couple of different driving rates. So a driving rate of 13 microns per second and a driving rate of 4 microns per second. Oh, and I should mention that the boundary conditions for this, as I'm showing you here, is a constant normal stress boundary and a constant shear rate boundary condition. And that's where these two driving rates come from. So this, again, I want to stress on the point that this is very, very close to the bifurcation or the stiffness stability boundary. And you can see this far from periodic behavior where you have a multitude of stress drops, events that become bigger and then go away, and you have small periods of stable sliding in between them and so on. So this super rich diversity in behaviors. This is also slow slip events, and the reason I call them slow is because the coseismic duration of these is comparable to the interseismic, and the fault slip rates from these experiments are also quite close to the background loading rates. So these are very, very slow events. So we simulated these experiments in a 1D numerical model of the fault, where instead of assuming that the fault is a rigid block, we make the fault in our case is made up of a deformable mesh of elements. And so we take the fault thickness explicitly into account in the calculation of the elastic loading rates in the strain history. And the frictional forces are imposed at the shear boundary in blue as shear tractions. So basically, we're solving a force balance that includes elastic compressional loading of the spring, shear loading of the fault, both of which are balanced by radiant state friction shear traction at this blue boundary, as well as radiation damping. The force balance between the mesh elements is then solved using an explicit Lagrangian technique called FLAC, which is actually a pretty popular method that has been used in geotechnical and civil engineering for over, I don't know, 40, 50 years at this point. So in the next slide, I'm going to show you the results of what happens when we do this. We took the friction parameters of the quartz gouge and the boundary conditions of our lab experiments and imposed them on the numerical model of this deformable fault. And it only has one state variable friction. And what we see is it does an excellent job of simulating the lab data, particularly the stress drop systematics, the recurrence interval, the slip speeds, the chaotic nature, the aperiodic nature of the lab data, and so on. And yeah, so the numerical model is in green. So on this left here is a plot of slip duration and total coseismic slip. And on the right is a plot of the slip duration versus the average stress drop on the fault for these events from the lab as well as from the model. The green data are from the numerical model, and the purple data come from the lab experiments. And we have fewer purple dots than green dots because the lab experiments were run for a shorter amount of time than the model. So there's more data in the model, more stick slip events in the model. But overall, what you can see is that the numbers are quite consistent across the lab data and the numerical model. So then the next natural question for me is what causes these chaotic ruptures, even on the simple and perfectly homogeneous lab experiments and numerical models? We don't have any installed heterogeneities of any kind, be it geometric, material, or whatever. So we can take a closer look at this. and the space-time variations and rupture patterns in the model, we don't have the same luxury in the lab because all of these quantities are measured in a fault average sense. So on the left is a plot of distance along the fault, in this case 5 centimeters, and y-axis is time. So the deep purples here mean that the fault is locked. The white areas represent creep, and the green areas represent coseismic slip. Now, because the slip duration is short relative to the y-axis, it's kind of hard to see the green coseismic slip, but typically you have to believe me that they generally follow the locking. What we observe is that local stress heterogeneities from previous ruptures seem to modulate the future ruptures. And so you can also see migrations if you follow some of these white trails here. Another way to look at it is in the plot on the right, I have local variations in slip velocity and shear stress at 5 different locations along the length of the fault from 5 to 45 millimeters. And you can really see these migrating rupture patterns. So for example, if you consider the dark blue here, it's kind of stably creeping, whereas if you take orange at the same time, it is stick slipping. So different portions of the fault are doing different things essentially. So if we believe that this is what is going on in the lab experiments as well, what this implies is that even the smallest lab faults are not necessarily rigid slider blocks and may be fully capable of hosting confined ruptures under certain specific conditions, which I think is really neat. So now I'm going to try and combine this numerical modeling framework with this idea that the critical slip distance encodes information about the shear zone thickness. So this is all super new work, so kind of bear with me. So scaling this model up to slow slip events in a natural fault, we're making a couple of assumptions here. We're saying that during a slow slip events, smaller fractures and faults and brittle lenses in a shear zone may experience elevated strain rates because of 2 reasons. So the strain rate is simply the ratio, in this case, of the loading velocity divided by the width of the shear zone or the width of the fracture and so on. A smaller fracture or a smaller structure, thinner structure, is going to have a smaller width. And the structures that are embedded in the larger shear zone are probably, during a slow slip event, for example, being loaded at transiently elevated velocities. So the information about the shear zone width is explicitly incorporated in the loading rate term, in the strain rate term, and information about the shear zone width is incorporated into our radiant state friction in the form of d sub c, where the critical slip distance takes the form of some direct proportional relationship between it and the shear zone width. And for simplicity, we just assume that there's a linear relationship, so n equals 1 here. Although that's not strictly required for these results to work, it just makes my life easier, that's all. So in the next few slides, I'm going to show the results from a series of what I call nested numerical models. And what I mean is that starting from the largest fracture, which is deep blue, which is going to host slow slip events, the peak slip rates experienced by this fault loads this fault, and the maximum slip rates experienced by this fault loads this fault, and so on. So each fracture is subsequently smaller than the previous fracture, and it's being loaded by a slip rate that the next bigger fracture is experiencing, and so on. And simultaneously, because the fractures are smaller, they have smaller widths. So basically going from deep blue to deep red, you have elevated strain rates that the fault or fracture is being loaded at. And so when we do this, what we saw was really interesting is that we're basically recovering a spectrum of event durations on the same fault with the smaller fractures that are generating events with lower moment than the larger fractures and so on. And the slip durations for these fractures are entirely consistent with, silent slow slip events, VLFEs, LFEs, and so on. And so what I'm trying to make a case for is that basically within the same fault zone, different structures experiencing a range of strains and strain rates and so on, having a variety of d sub c's or critical slip distances, are able to exhibit a variety of slip styles, which I think is really neat. And all we had to do was vary the critical slip distance simultaneously with the fault zone width in some fashion. Okay, So just to summarize this portion of my talk, what I've showed you is that we are able to generate complex ruptures in very simple homogeneous experimental faults, which have no pre-installed geometric or lithological heterogeneities. We are explicitly considering the fault zone thickness in our numerical simulations as part of the loading rate calculations. And this results in confined ruptures in what we always previously used to think are rigid block friction experiments, even in the tiniest laboratory faults. And taking all this information and scaling it up to larger fault zones, if we scale the fault zone thickness with the critical slip distance, which we think is a proxy for fault zone thickness, it is able to reproduce a range of slip modes for the same fault or for the same frictional material, all else kept constant. So with that, I will just provide a broad summary of everything I've said. First, we talked about fault healing, taking the example of the Northern Hikurangi margin, and I showed you how we can get slow slip events there. And then we moved to the lab and generated slow slip events in the lab and confined ruptures in laboratory experiments. And so with that, I will stop here. I think I'm at 45 minutes and I will take any questions. Thank you so much.